Oh, yeah. And I'm actually going to say, again, as I did yesterday, it's going to be between 0 and 1. So we would realize it can't be negative. Remember that the growth factor, just from yesterday, is when b is greater than 1. So the first 4 examples ask us, is it exponential growth or is it exponential decay? Without graphing it. So all we have to do is look at the b value and ask ourselves, is this greater than 1 or less than 1? So 2/3, it's 0.6 repeating, that's less than 1. So this has to be exponential decay. Make sure you're only looking at the b value. The initial population doesn't matter at all what a is. It's just what b is. So the next one would be what? Growth or decay? Here, decay. Number 3 would be? Abby? Growth. 5 is greater than 1. And the last one. Ashley? Decay. All right, so I've talked about this word briefly when we were looking at a graph of a rational function. And here's our formal definition. An asymptote. An asymptote is a line that a graph approaches, but it never actually reaches. So here's a example of a horizontal asymptote. It's an imaginary line. You wouldn't actually see it. Now, some of your graphing calculators will show a solid line, but it's not actually there. So again, the curve, usually when we do exponential, we have the x-axis, and the curve goes either up or down. But it would get really close to y equals 0, but it never actually touches it. Okay, it gets really, really small. And that would be an example of a horizontal asymptote. A vertical asymptote we're not going to see as much, but we will, where will get really large, but it won't actually touch like that certain number. And these are going to be more when we get to rational functions. Okay, but we will see the horizontal asymptotes today. All right, so graph each decay function, identify the horizontal asymptote. Notice they already scaled the graph for us. So let's do this one without a calculator again to see if we can. Now, to do this without a calculator, I would probably change my 0.5 to a 1/2. So we'll plug in, and I left space over here so that you can do your work. Start with our -3. Now, when you have a fraction being raised to a negative exponent, remember you can just flip the fraction, take the reciprocal of it, and make that a positive exponent. Then perform our order of operations, which are exponents first. And then you can multiply 36 times 8 off to the side, and we'll get 288. So since these are decay problems, they are going to start out with larger numbers, and then they're going to decrease to smaller numbers as we go. One after the 0 is just 1, so that one's easy. That's just 36. See if you guys can complete the rest of the table and plot your points. But we'll always be, and we'll abbreviate that HA, or horizontal asymptote, will always be at the line y equals 0, which is also the x-axis. Straight line at 0. That's again because it's never going to go below 0 or equal 0. It's just going to get really, really small. So it'll be like scientific notation small. Do you think we need to do another one of these? Or do you kind of, I mean, you're going to practice them on your homework. Do you want to skip these two then? Sure? Okay. We have time, we can go back and do one if anyone wants. The word problems are going to be about decreasing rates now. One of the biggest things that you'll see in terms of the decrease rates is when you buy a car. So when you buy a car, as soon as you drive it off the lot, it depreciates in value, right? Because you've traveled it miles. So a lot of the problems will be about depreciation of the value of the car. So exponential decay graph shows the expected depreciation of a car over 4 years. So you can see that it's going down. Estimate the value of the car after 10 years. Now, the decay factor, which is the same as the growth factor, is B equals 1 plus R. But R is going to be a negative number because it's a rate of decrease. So anytime you see a rate of decrease, you'll have to insert a negative in front of it. So if it says it's a 10% decrease, that's negative 0.1. Now, they don't give us the rate. Normally they will, but they don't. So we have to actually figure out what R is. They tell us that the initial value of the car was 20,000. Whoops. And you can see that in the chart. And then after the 4 years, or excuse me, after 1 year, it was about 17,000. So we can calculate the value of R by just subtracting. So the final value was 17,000 minus the initial value was 20,000, all divided by the initial. So you always divide by the original whenever you're doing percent change. You guys might even see this in bio and chem, when you're doing your percent change. Well, you should get negative 3,000 over 20,000, which will get me negative 0.15. And again, that's my R. Then we have to find our decay factor, RB, which is 1 plus R. Yesterday it always became a positive, greater than 1 value. This time it'll become less than 1 because we have a negative. So we'll get 0.85. And then we're asked to write a function. So again, our standard form for a function is y equals a times b to the x. Remembering that a stands for the initial, it was population yesterday. This will be today the initial value of the car, starting point. So this will be 20,000 times 0.85 to the x power. And x would be standing for the number of years since you purchased the car. So this one is kind of defined for you because it's in the graph. And then last but not least, we're going to evaluate this for finding the cost of the car at year 10. And then that all goes in our calculator with our caret key. And we should get 3,937.4. No. It's not worth a whole lot. And then we have a few more application problems on the back. One more depreciation, and then we have some with population, and they're kind of mixed, growth and decay, so that you guys can kind of have to think about it. Now the next one is still a depreciation, but they don't give us the values. We don't have to calculate R. Suppose that you want to buy a used car that costs $11,800. So this is your initial cost, which is our A. The expected depreciation of the car is 20%. So you need to infer that that's a negative 0.2. So as soon as you see the word depreciate or decrease, you have to insert the negative. Estimate the depreciated value of the car after 6 years. So we have to do all the steps that we did on the first part. We have to find our B, write an equation, and then we'll sub in 6 for the equation. So B is equal to 1 plus R. So 1 plus a negative 0.2 will tell me that my B value is 0.8. And if you could do that in your head, most of you can't, you don't have to write out the work. 100% minus 20% is 80%, B is 0.8. But I'll show it on the board just so you know where it's coming from. Then we'll write our general form equation. I should just mention while we're here, a lot of you will get the depreciation questions wrong because you will put 1.2 right here. So just make sure that when you're reading, depreciate, decrease, make sure you put a negative. And make sure that it makes sense at the end of the problem when you look at your answer. All right, now we'll plug in 6 for x. Well, they didn't say I had to write the equation, so you don't have to define the variable if you don't want. The only thing they really wanted for this one was the final answer. And what do we get? Caleb? You got it. All right, I'd like you guys to read through examples 10 and 11 and see if you can come up with an equation, and then also use that equation to estimate the value. And then we'll go over that. All right, see if you can do the closure, which is kind of the same but has bacteria doubling, and see if you can